How do you solve a problem like dark matter? Or explain why the universe is built the way it is? For physicists, there's been one answer that has worked for nearly 100 years. Take two particles and smash them together as hard as you can. That's what happens at enormous particle accelerators like the Large Hadron Collider at CERN. As Einstein showed with E equals mc squared, energy can turn into mass. So if you collide your particles with enough energy, you can create new particles. That's how researchers first saw the Higgs boson in 2012. But it looks like the LHC is not going to create the floods of new particles that some physicists expected. So researchers are looking to a new kind of discovery machine, able to reach even higher energies and colliding particles that haven't been used in an experiment like this before. Muons. Muons are from a group of particles called leptons. Like their cousins electrons, they're negatively charged. They're just much heavier. And they're fundamental particles, meaning they can't be broken up into anything smaller. In collisions, this is a huge advantage over protons. Protons are what's smashed together at the LHC today and would eventually collide at CERN's Future Circular Collider, a new machine the lab is proposing for the 2070s. But in a collision between protons, energy gets divided between the quarks that make them up. Each collision is actually a quark-quark collision. Because muons are already single points, all of their energy gets focused into every smash. That means you can use lower energy collisions to produce the same high energy particles. So your collider can be smaller and much cheaper. Electrons are also fundamental, but muons have a big advantage over their lighter cousins. When you try to accelerate electrons around a curve, they lose energy to something called synchrotron radiation. That cuts the energy you can accelerate them to, and means that to reach extreme energies, you need a long, straight track. The muons' heavier mass, compared to their charge, means they shed much less energy this way. So a muon collider can be circular and reach super high energies. And a circular smasher has other benefits, like being able to host multiple experiments and give particles many more chances to collide. All of this means that a muon collider could deliver the same science as a proton machine, but in a compact ring around 10 kilometers in circumference, and for a cost of around $18 billion. That's not cheap, but it's much less than the $50 billion another proton collider would probably cost. In fact, it's about the same as a new electron collider, which physicists hope to build to do precision studies in the more immediate future. So it sounds like building a muon collider is a no-brainer. Well, while the muon collider concept has been around since the 1960s, in reality, making one is far from straightforward. That's because muons are a bit of a nightmare to work with. They're unstable, meaning they live only fleetingly for milliseconds. And this makes it hard to focus them into a beam and accelerate them before they decay into other particles. Technologies that can do this are still being designed. There could even be an environmental impact, with a small fraction of the neutrinos produced by muon decay hitting atoms kilometers away and creating harmful radiation. But some physicists see these technical hurdles almost as a positive. Finding solutions means inventing new technologies and inspiring a generation of scientists. A muon collider might be a compelling and relatively affordable alternative, if researchers can show they can make one work.